my name is Caroline Jones, and my group and I will be proving the extended law of sines. Before we go over the theorem and the proof, though, let us first go over some important information that you'll need to know. Let us start with the law of sines. If you'll look at the blue triangle, triangle ABC, you'll see that A, capital B, and capital C all denote angle measures, and lowercase a, lowercase b, and lowercase c all denote the side lengths opposite those angles. I've also drawn an altitude from angle A and denoted it as h. If we go by the rule of sines, which if you take a sine of any angle measure, it's equal to opposite over the hypotenuse. So you'll see that with our blue triangle, we have sine of b is equal to h over c, and sine of c is equal to h over b. If we solve for h, we get that h is equal to c sine of b, and h is also equal to b sine of c. Since both of these equal h, they also equal each other. So we set them equal to each other, and then we can divide each side by sine of b and sine of c, giving us c over sine c is equal to b over sine b. Similarly, I've also drawn a pink triangle, triangle ABC, where capital A, capital B, and capital C denote angle measures, and lowercase a, lowercase b, and lowercase c all denote the side lengths opposite those angle measures. This time, though, I've drawn the altitude from angle B. And as I said, similarly, we get a over sine A is equal to c over sine c. Now, putting these two together, we get a over sine A is equal to b over sine b is equal to c over sine c. And that is the law of sines. Another thing you'll need to know about that before we can go on to the theorem and the proof is what a circumcircle and a circumradius is. The circumcircle, any circumcircle is unique to the triangle that it is drawn around. Well, any triangle can only have one circumcircle. So the circumcircle in this case is the orange circle that is drawn around triangle ABC. Now looking at the circumradius, we have the circumradius is the length of the radius of the circumcircle, and I've denoted that as r. And then one more thing, we also have a circumcenter, which is just the center of the circumcircle, and I've denoted that as O.
Hello, my name is Paul Lee, and for this extended law of sines proof, we will go through the theorem that states that every triangle has a circumscribed circle or circumcircle. So, given a triangle ABC, you can first construct the perpendicular bisectors of sides AB and AC. These bisectors will intersect at a point O. So, after we have created those two bisectors, we have that OD is perpendicular to AB, and also that OE is perpendicular to AC. Now that we have these two perpendicular sets of lines, we can actually prove two similar triangles. We can say that triangle ODA is congruent to triangle ODB by the side angle side theorem. Thus, OA is equal to OB because they are corresponding sides of congruent triangles. It is also the case that triangle OEA is congruent to OEC by the side angle side theorem. So we have that OA is equal to OC because it is the corresponding sides of congruent triangles. Now we can consider any point on X on segment AE. We find that from Pythagorean theorem, OA is equal to the square root of OE squared plus EA squared, which is also equal to the square root of OE squared plus EX plus XA squared, which is greater than the square root of OE squared plus EX squared, which is equal to OX. And from all of this, we know that OA must be greater than OX. Similarly, we can also establish that the radius R is equal to OA, which is equal to OB, which is equal to OC, and that it is greater than the distance from O to any other point Z on triangle ABC. Therefore, the circle with center at O and radius R circumscribes the triangle.
Lowercase a, lowercase b, lowercase c to denote the lengths opposite of the vertices A, B, C. Then a over sine of a equals b over sine of b equals c over sine of c, which equals 2r. So if you look over at the picture, we've drawn triangle ABC, and we've drawn its circumcircle. So we're going to now draw a point P where if we connect B to P, we can actually we can then name that the diameter of the circle. So, and I've drawn a point O to be the center of the circle, and I've also drawn from point C a line CP. So I went ahead and also denoted BC as lowercase a. It'll come in handy later. So we're going to denote the R to be the radius of the circle. And so for this proof, there's going to be three cases that by solving all these three cases, we're going to get the same thing, thus proving our theorem. So for the first case is for when angle A is less than 90 degrees. So since we've denoted BP to be the diameter, then we can see that a triangle PBC is actually a right triangle since BP is the diameter. So BP is going to be our hypotenuse, and so with some trig we know that the sine of P is going to equal BC over 2R, but we just denoted it as A, so it's going to be A over 2R. And with some algebra, we're going to get A over sine of P equals 2R. So if you look up at the picture, you see that actually angle P subtends the same arc as angle A. As you can see, it both lines going from point P and A connects with B and C. So they subtend the same arc, so therefore the angles are actually going to be equal. So therefore A over sine of A actually equals 2R, and that helps prove that case. So now we're going to go over the second case for if angle A is 90 degrees. So as you can see in the picture, we have our base BC is going to be our diameter of the circle, and then angle A, therefore angle A is actually going to be 90 degrees. So BC is now going to be our hypotenuse, which we're going to denote as lowercase a. And as the same thing from above, we're going to get sine of A, or I'm sorry, we know that A equals BC, which is the diameter, which is 2R. And since A is actually 90 degrees, we know that the sine of 90 degrees just equals 1. So if you take A over sine of A, since sine of A is 1, it's just going to equal 1. It's just going to equal A, which is therefore going to equal 2R. So then that helps prove our second case. Now we're on to our last case, which is when angle A is greater than 90 degrees. So in the picture, we've again drawn the circumcircle for triangle ABC and took the diameter from B to point P. So BP is going to be our diameter, and BC this time is going to, or BC is going to be labeled just lowercase a. So since BP is our diameter, triangle BPC is a right triangle, and so so therefore we know sine of P is A over 2R, since BP is our hypotenuse and is 2R, and therefore A over sine of P equals 2R. So, but as you see in this case, angle P and angle A aren't actually equal this time, but you have points A, B, P, and C are actually a quadrilateral, and it is an inscribed quadrilateral since it's inside the circle. And since A and P are opposite angles, they're actually going to be supplementary. So angle A equals 180 degrees minus angle P. And since we're working with sine here, if two angles are supplementary, then the sine of one angle is actually going to equal the sine of the other angle. For example, we know that sine of 30 degrees is 1/2. Well, 30 plus 150 equals 180 degrees. So 150 degrees is a supplementary angle to 30 degrees. and the sine of 150 degrees actually equals 1/2 2. So that's just one example. So therefore we know that sine of A equals sine of P. So therefore A over sine of A equals 2R, thus proving our third case, and therefore we can say A over sine of A equals B over sine of B equals C over sine of C equals 2R.